Hi everybody, today we're going to be taking notes on 2.3.3, Applying Properties of Triangle Similarity. Go ahead and turn to page 67 and we'll start taking notes. Today we're going to be talking about a lot of different proportionalities you can find in triangles and in parallel lines. So the first thing we're going to take a look at is the triangle proportionality theorem. Here's what it is. It says, if a line parallel to one side of a triangle intersects the other two sides of the triangle, then those lines divide the sides proportionally. Now don't freak out. You can pause the video. This is a lot to copy down, but let's try it. I'm going to read it one more time for you. If a line parallel to one side of a triangle intersects the other two sides of the triangle, then those lines divide the sides proportionally. Now before you get too afraid, let's draw a picture of this. So it says you have a line that's parallel to another line and it hits the two sides of a triangle. And it says if that happens, if these lines are parallel, then it's going to divide the sections of the triangle proportionally. So we're going to pretend that that segment is A, this segment is B, this top segment is C, and the segment down here is D. Then we could say that A over B is equal to C over D. Now if you need to, pause the video to take a moment to copy down the diagram and the theorem. When you're ready, unpause the video so that we can copy down the converse of the triangle proportionality theorem. Okay, so the converse of this triangular proportionality theorem, so it's kind of like the reverse, it's a little bit shorter. Here's what it says. If two lines divide a triangle's two sides proportionally, then you can say those two lines are parallel. So it's kind of the backwards of this one. So here's what it means. I'm going to go ahead and bring this down a little bit. Again, it says, if two lines divide a triangle's two sides proportionally, then those lines are parallel. So for example, if I had a triangle like this, and I said that this piece was 5 inches, this piece was 7 inches, this piece was 6 inches, and this piece was 3 inches, if I tested the proportion, 5 over 7 and 6 over 3, these are not proportional, so I know that these lines right here are not parallel. The converse of that might look like this. Suppose I had a triangle where the side lengths look like this instead. 3 and 3.5, 6 and 7. We could do a test of 3 over 3.5 and 6 over 7 and ask ourselves, are these equal? Well, they sure are. In this case, these fractions are equal, so I could conclude that these two lines are parallel. So what we're going to do today is we're going to be using the triangle proportionality theorem and its converse to talk about and find the missing sides of a triangle or to show that two lines are parallel. Let's give this a try. So for example 1, let's go ahead and read it together. It says, suppose UY, line UY, is parallel to line VX. UY is parallel to VX. Then it says that UV is 3 and UW is 18. UV is 3 and UW, this whole length right here, is 18. And XW is 16. XW is 16. What is the length of YX? Okay, so I know by looking at this picture that this whole length is 18, but I'd like to know what this piece is. How do I find it? Well, VW is going to be the whole length of 18 minus this little piece here. If you take this whole length and you take out that 3, you would get 15. That's why this side is 15. And that makes sense because if you added up 3 and 15, you would get 18, right? Okay, now since I know that these two lines are parallel, then because of the triangle proportionality theorem, I know that this side divided by this side should equal this side divided by that side. Piece divided by piece equals piece divided by piece. Let's look at that. Piece divided by piece, that's the top pieces, should be equal to the piece over the other piece. These are just little chunks of the triangle. This side divided by this side divided by this side. We've been solving proportions all day long. So 3 times 16 is 48, and 15 times x is 15x. And when you divide by 15, I'll be your calculator today, you get x equals 9.6. Now you're going to go ahead and turn the page, and we're going to take a look at example 2. Now, I put these on the same page because I wanted you to notice that example 2 and example 1 are a little bit different. Example 2 says this: determine if PQ is parallel to TR. They're asking us, are these two lines parallel? That's different from this problem. This problem starts with this line and this line. They're parallel. So here they say they're parallel, and here they're asking us to prove that they're parallel. So this is asking us to use the converse. They're asking us to prove that if these two are proportional, if these sides are proportional, then I can conclude that the lines are parallel. So let's check it out. Is 8 over 3 equal to 24 over 9? If it is, then I can say that PQ is parallel to TR. So that's what we have to check. Well, let me ask you, is 8/3 the same as 24 over 9? You could pull out your calculator, but I'm going to go ahead and squeeze your brains a little bit here. If I simplified this fraction, the second one, by 3, what would I get? I'm going to keep 8/3 the same, so that fraction has stayed the same, but 24 divided by 3 is 8, and 9 divided by 3 is 3. That means that these two fractions are indeed the same. And if they are, then I conclude that PQ is parallel to TR. Now for our last example using the triangle proportionality theorem. Now for example 3, they start by saying that the two lines are parallel. So I know I'm going to use these. Since those two lines are parallel, I know that the sides are proportional. 8 is proportional to 2, as x is to whatever this is. So let's see what they've given me. JH is 12. So that means this whole side is 12. Well, here's my problem. I don't know what this piece is. And if I did, I would write the proportion 8 over 2 equals x over, well, whatever this red piece is, right? 8 over 2 equals x over this piece. But I don't know what it is. I do know what this whole thing is. It's 12. Let's just do like an exercise of the mind here. If the whole thing is 12, let's just pretend for a second that this piece was 7. If this was 7, what would this be? Did you say 5? I think you did. 7 plus 5 is 12. That makes sense. 12 minus 7 would give you 5, right? What if this was 4? What would this piece be? If this was 4, this would be, what are you doing in your head? Are you saying in your head 12 minus 4 would be 8? That's right. Whatever number I pretend this is, in your brain you're always saying 12 minus this number gives me this. Well, you just figured out what this piece is. If you want to know what JL is 12 minus x. That's what that is. It's the entire piece minus this portion. So I'm going to put 12 minus x in that part. Okay, let's go ahead and solve this proportion the way we normally would. First, I'm going to multiply 2 times x, which gives me 2x. And then I'm going to multiply 8 times this quantity. So 8 times the quantity 12 minus x. I get 2x equals, okay, 8 times 12 is 96 minus 8x. Now I'm going to add 8x to both sides. So I get 10x equals 96. And if I divide by 10 on both sides, I'll get x equals 9.6. Okay, now we're going to take a look at a new theorem. This is called the two transversal proportionality theorem. It's the two transversal proportionality theorem. Sounds worse than it is, trust me. Here's what you're going to write down. The two transversal proportionality theorem is if 3 or more parallel lines intersect two transversals, if 3 or more parallel lines intersect two transversals, then they divide them proportionally. Then they divide them proportionally. Let me give you a picture to draw while you're still copying this down. So I want you to imagine that you've got 1, 2, 3 parallel lines. Let's show that they're parallel. And they're cut by two transversals. 1, 2 transversals. Then they've been divided proportionally. So we'll say that this length is A, that's an A, B, C, and D. Then I can conclude that A over B, why is my A's coming out so ugly? A over B is equal to C over D. So I hope you're seeing how similar this is to the triangle proportionality theorem. The only difference would be that these transversals would go up and actually close to make a triangle. It's basically the same theorem. Let's try this one on for size. So in example 4 at the bottom of your page, here's what it says. In the diagram, angle 1 is congruent to angle 2 is congruent to angle 3. Let's mark that. Angle 1 is congruent to angle 2 is congruent to angle 3. Now all of these angles are to the right and down. So they're lower right, lower right, lower right. What type of angles are those? Angles that are all in the same location? Oh, corresponding angles. That's right. All 3 of these angles are corresponding and they're congruent. Why? Because those angles are congruent, well, that means that these lines must be parallel. This is one of the ways you can prove lines are parallel. If the corresponding angles are congruent, it proves the lines are parallel. So that means this line is parallel to this line is parallel to this line. Now we need to say that they're parallel because if they're parallel, then I know something. I know that these little pieces in here have been divided proportionally. So let's continue reading. AB is 6. AB is 6. BC is 9. And EF is 8. And they ask, what is the length of DE? That's an X. So let's set up our proportion. 6 over 9 should be proportional to X over 8. And I can say that because I proved those lines were parallel. So let's do our math. 9 times X is 9X, and 6 times 8 is 48. I'll be your calculator. Divide by 9 on both sides, and you get 5.3 repeating is what you're going to get for X, or 5 1/3. Okay, go ahead and turn the page, and let's look at our next problem. So for example 5, we're going to again use our statements here about knowing that if these lines are parallel, I know something about these segments. So it says the 3 horizontal lines are parallel, so I'm going to mark those parallel. And if they're parallel, then I know that these segments have been divided proportionally, or that 20 over 8 is proportional to 15 over x. They are equivalent fractions. Okay, let's multiply 8 times 15. 8 times 15 is 120. And 20 times x is 20x. If you divide by 20 on both sides, you'll get x equals 6. That means that this little section down here was 6. You're looking good, guys. Here we go. Last theorem of the day. This is the triangle angle bisector theorem. Try saying that 3 times fast. The triangle angle bisector theorem. It's a long one. Sorry, guys. An angle bisector of a triangle divides the opposite side into 2 segments whose lengths are proportional to the lengths of the other sides. Here we go. The triangle angle bisector theorem says that if you have an angle bisector of a triangle, that angle bisector divides the opposite side into 2 segments, and those lengths are proportional to the lengths of the other side. Let's draw a picture so that we know what this looks like. If you have a triangle and there it has an angle bisector. Now an angle bisector means that when it comes in, it cuts the angles in half. That means that this little angle right here is equal to this little angle right there. And what it's saying is that the angle bisector, it divides this opposite side into 2 lengths. We'll call those lengths A and C. And it says that those sides, those lengths, are proportional to the lengths of the other sides. So sides B and sides D. So A over B is proportional to C over D. This little chunk that's been divided is proportional to the side closest to it, and this other side that's been divided is proportional to the side that's next to it. Those are the relationships. So in example 6, for example, it says that ABD, so this angle, is congruent to DBC, this angle. So let's find those pieces. This is my A and my C. This is my D, and this is my B. That means that 6 over x is equal to 8 over 20. This side over this side closest to it is equal to this other piece that's been divided by the angle bisector and the side that's closest to it. To solve this, we multiply to get 8x equals 120. Divide by 8 on both sides to get x equals 15. Okay, how about example 7? They're saying that the angle LKM is congruent to the angle MKN. Here's my angle bisector then. Now they're giving us some measurements. They say that LK is 9. LK is 9. They say that KN is 15. KN is 15. And they say that MN is 5. MN is 5. What is the length of LM? So what would be the proportion? It's divided these two sides, it's divided this side into 2 pieces, and each of those has a relationship with the side closest to it. So x over 9 has a relationship with 5 over 15. When we multiply to find our answer, we'll do 5 times 9 to get 45, and x times 15 to get 15x. 15x. And when you divide by 15, you'll get x equals 3.